So I'll start off with the introduction of when I learned about Julia, or what happened with that. I'm with Foreo, and Foreo started in 2001, and we started as a simulation company. So we do dynamic simulations and discrete event simulations and publish them online, basically sharing them with all kinds of groups, sometimes for forecasting purposes, sometimes for like training, things like that. And as our company evolved over time, there have been people who have been interested in solving analytic problems, and we kind of force it in. We'd use Java to create something on the server to be able to do those kinds of problems for people. We had gone through a couple iterations of our platform over the years, one in 2002 and another one in 2008. And so we were kind of due for our third generation platform. We were beginning to look at it in the winter of 2012, so in January 2012. And what we were doing is sort of having a bake-off. We tried a number of languages. We were trying MATLAB, Python, R. We tried Lua for fun. We had a couple other things in there. And you can see here, here's an email that was from a colleague of mine who was writing in kind of talking about, I don't know how well you guys can read this in the back, but it's basically an email about here's some things that estimating development hours for including something like this as a service on our platform for MATLAB. And here's for Julia, or excuse me, for Lua. And we were having some success with this. What we ended up doing was writing the same algorithm in multiple languages and kind of testing it. And our big criterion for it was, well, partly speed, that was important, but a big one was expressiveness. So, we were using this ourselves, and we were hoping that our customers would be using it as well. And then, of course, as Yuri mentioned a moment ago, we saw this post in Hacker News, which I guess probably originated in Reddit and then came to Hacker News or something.
That's right.
In February. And people said, hey, we should check this out. We did some research on it, and many months later, I'm standing in front of you today. So that was sort of the progress with it. What I want to do is talk about a little bit, sort of where we've taken this in terms of building some things out for making models essentially available to non-experts. So, the basic reason for Foreo to exist is this idea that, modelers and data scientists can spend weeks and even years of their lives creating something, and often it'll only get seen by like a dozen people or something. And it's because of this issue of accessibility, right? So if you're working in this is Julia's studio here, you're developing something, and you say, I'd like you to experiment with changing some assumptions with something that I've built and to rerun it. And if that person hasn't any experience in IDEs or in Julia, there's a lot that person will need to go through in order to try out that experiment. So there's this accessibility thing, and that the only people that would be willing to do that are people that that know you well and that sort of believe that investment of time of at least 30 minutes, but maybe longer, is going to pay off in terms of being able to build something else. But there's a much broader audience in terms of orders of magnitude more people that can be reached if you can get something that's accessible in a couple ways. One is accessible in the sense of they don't have to install anything. All they have to do is go through, say, putting something on a tablet or running something through the browser to see it. But there's sort of another expectation in terms of accessibility too. One is, they're going to be able to quickly comprehend what it is that they need to do. But another one is sort of in terms of speed again, right? So there's an expectation if you're running something online that things are going to run reasonably fast. So they're not going to take, certainly not days, certainly not hours, not even minutes, or so it has to be very quick. But there's this nature of performance that we're often talking about with respect to scientific and computing languages that has to do where we almost ignore time. We look at it as sort of what's the when we look at a speed of solvers, which is what this is doing here on the traveling salesman problem. You look at it in terms of the performance is measured in the number of cities it calculates, but it says nothing about the number of how long it took to calculate this or what kinds of hardware were used to do this. And I think actually this list is extended now to 80,000 or something like that, but the same group with Applegate, maybe someone here knows. But in any case, this is sort of a different issue with respect to timing and things. And there's actually a reason why sharing this stuff online can make it more valuable, sort of solving a different kind of problem. And there's this piece that I read about this winter. It comes from this book, In Pursuit of the Traveling Salesman. where this guy, H.M. Cleveland, in 1925 was doing his salesman route for the Page Seed Company in Maine. And his headquarters was working with him, trying to come up with the most optimum route for him to complete. And they had this piece of paper, this yellow piece of paper that was typed up with these this list of cities that he was supposed to visit. And after he received this, he sent a note back to headquarters, and he said, "Dear sirs, my route list is balled up, the worst I ever saw. Will take half as long again to work as last year. And I wish you would send me my old list from 1924 from Dexter, as it is much better than this. The river from Bangor down has no bridge, and you have those towns down as if I could cross anywhere. Last season's list was made out the best of anyone, and I can't see the object of changing it over. I think I have made myself plain." Really, H.M. Cleveland. So, he faced this issue, and it sort of illustrates a problem of distributed analytics or distributed solvers, in that he's facing something that they couldn't really anticipate, certainly not in 1925, or they couldn't do much about at least. Now, one is that conditions change. The bridges can go out, that roads change, that traffic conditions can change. The other problem is that the user essentially is geographically dispersed. That H.M. Cleveland needs to be able to travel around and to ideally adjust things as he's moving around things. And he needs solutions fast as conditions change, as something goes on in terms of a bridge going out, possibly traffic, that there needs to be an update. And the company, Page Seed Company, needs something for a distributed state-of-the-art solution. So this has been heating up a bit recently with modern internet-based delivery, right? So this is growing a lot in the last year especially, but even before that, for some places like Amazon Fresh and Google Shopping Express, but also local ones, like local florists are doing a lot more of this and things. And clearly there's a need in here for large-scale solvers that are running on powerful computers when doing this. If you imagine a place like, say, Google Shopping Express, you've got this problem. You have hundreds of trucks, and you've got literally thousands of orders that need to be cleared in a 4-hour window, and it's a big problem. It's going to take a lot of power to solve that problem, to do it efficiently. But what you're going to do then eventually is you're going to say, okay, each truck gets, for that 4-hour window, maybe 20 or 30 packages to deliver, and then they're on their own. That's pretty much set. But once the driver has started the delivery route, the optimization problem changes, right? And so the problem becomes something a bit different. It's, and you can't solve it on centralized delivery. It can't be easily updated. The problem initially is based on distance, but maybe it should be based on duration. And it does not include real-time data on traffic. So potentially distributing online is a way of resolving this, where you need to be able to handle thousands of geographically dispersed delivery people, runs in seconds, and can access current traffic data. So we've been working on some things related to this, and let me just switch this around. So here we have a geographic-based solver running with Julia under the hood, and we just put in sort of a route here, sort of a list, arbitrary list of businesses in the San Francisco area over here on the left, and map them out according to that from here. And then what we're doing on this side is solving it for the optimized route. And for this particular case, what we've done is we've seen a 32% savings in time here, gone from about an hour 25 minutes to 57 minutes, or a little under an hour, and a 35% savings in distance travel. Small savings in the longest segment, I guess, in this case. And there's some other fun things we can do with this too. So when we built this out, we were kind of saying, well, at the time, just about a month ago or so, there was a San Francisco book crawl. And if for some reason you wanted to optimize your book crawl, you could run the optimizer for that. There's another one for doing sightseeing tours in the Bay Area. And you can calculate the best route for that if you wanted to efficiently explore San Francisco. And then, of course, what else you can do here is put in some personalized travel plans. So where are we now? We're in Bleacher, is that right? Yeah, that looks like that's it. You could go from there to, what was that place we went for lunch, Naf Naf or something like that? There it is, Naf Naf Grill. And let's say we go from there to the Hancock Building. And it's not called the Sears Tower anymore, is it? Something
Willis.
else? Pardon?
I think it's Willis.
Willis, there it is. Okay, actually comes up with Sears. That's good. And then I'll go to, where am I staying? The Hotel Felix. There we go. And then let's go to the Intercontinental. Something like the Intercontinental. All right. So then we can put those in and calculate the best route. And yeah, I get a little bit of savings from that. So that kind of works out for my Chicago route. And what's interesting about this too, or potentially useful anyway, is this ability then to save the route. So I can save this. I can call this my JuliaCon route. And save that to the server then. And then if I open this up in another instance, I can send this off to somebody else then. And they'll be able to run this and calculate this for themselves. So that's the idea. And this is built on a stack of technologies. What it's using is a lot of the things that we've seen presented here over the last few days. We've got JUMP as the algebraic solver, and then we're running, we've actually experimented this with a couple of things. We've used GLPK, we've also used CPlex for running it out. And of course, Julia on top of that, and then we're using some other technologies for hosting this and running this online from there. And what I thought I could do is just go through a little bit and show you how this is constructed. So this is kind of an outline of how this code works here. This is the user interface up here on the upper left. So there's some client-side user interface code that's written in JavaScript, and it's communicating with APIs for doing the maps and getting the current traffic information for duration data, for constructing a duration matrix, and then communicating back and forth with the server that's just running the Julia side code. So, you know, a simple case of that, which in the kind of the preset version that I was showing, uses some JSON, right? So here we go from Forio to the Golden Gate Bridge to the Palace of Fine Arts, some landmarks other than Forio in San Francisco. And here's longitude and latitude for that, and that's kind of how those points get in. But you can also get them in, obviously, by calling an API to generate them elsewhere. And once you've got that, the next step is to construct a duration matrix similar to the distance matrix. So something that looks like this. And fortunately, Google provides this API that's called distance matrix. And so this is what we're using for this. And it has some limitations to it. The big limitation is only 9 waypoints. So that's a major constraint for this demo here, but it can extend beyond that, obviously, with other tools. And then you put into it is you give it the matrix, and what it kicks out is a lot of different information. It's a JavaScript object that has duration information as well as distance and some text and things like that. And of course, that needs to be scrubbed and reorganized to create this. And what you can see here is an asymmetric problem too, as you'd expect within the city, right? Because you have lots of one-way streets, and again, you're going to have traffic information and stuff. So going from Forio to the Golden Gate Bridge takes a little under 13 minutes. Going from the Golden Gate Bridge to Forio takes a little over 13 minutes, and so on across the matrix. And so once you've got that constructed, the next step is to send that information to the server. And so this is the part where Epicenter kind of kicks in, and there's this thing called the operations service. And what it does is it calls a function in Julia called solve and sends it over that duration matrix. So that's basically the step in it. And after it has that, then it's using the jump code to construct the problem. And so here you can see we're using GLPK. And like I said, when we experimented with this for CPlex, it was all we had to do was literally just change the name of the solver, and it worked perfectly. It's very nice. So thanks, Ian. Then we set the objective function, and then set up a bunch of constraints for that, and then solve. We're extracting this tour here. So tour is just an index, and originally the index was 1 to 9 and back to 1 again. And what it returns is sort of the optimized indices in the correct order for the optimization. So that's the idea. So this is built on, with some other functionality behind it. So there's this calculation engine up here that communicates through this app server, and there's other pieces here that we're using in this project. For example, data to store the waypoints essentially, and also to store instances of it or sessions that can run across. But then there's also things that we're not using in this case that can be useful often, which is related to authentication and single sign-on and things like that. And there's a series of APIs that are communicating with both third-party services and also, of course, with the browser or some kind of mobile device and things. And then there's this sort of authoring environment for creating these things on this server. But the users here can interact through the browser with the mobile device. They can also get data through the server-side script. So just to give you a little bit more about how this all functions, this is the JavaScript code again for solving. I showed you this a moment ago, where you're saying pull this function solve and then put in the duration matrix. Then what we do is we call this wrapper for the TSP model. And so this is the TSP model here with tsp.jl. And then we use this thing called using epicenter, which, then we just expose the functions that we want to make available to JavaScript. So in this case, we have the solve function and then the result, which is indices for the tour. And from there, what we do is we just call this build function, which is within tsp.jl with the duration matrix, and then solve for it, and then return the tour and the indices. So it's pretty simple. So that's the basic code for it. Another problem that we kind of have to solve with this is the fact that it's not just a single instance. And Avik, I think, was talking about something similar earlier about this problem of having, I don't know where Avik is now. Oh, there you go. So of having it run on, I have multiple sessions run on a single server. So this is one of the things that we had to solve with this, is creating this distributed computation engine. This is sort of one of the things that we were challenged with when we decided to go with Julia as a platform, which really would have been a problem for any technical computing language. Because again, with our history of doing things in simulation, a lot of times the simulation, because they're sort of numerically simpler, or the calculation time is faster generally, you can get away with kind of putting a lot of stuff on a single server. Whereas here, you really need to be able to have your model session sandboxed entirely, completely for it to work properly. So that's what's happening here, and that's sort of a new configuration, new architecture for the platform. And what it does is it just creates virtual servers as needed. And we've experimented with that for these series of problems. We've run it up to, I think so far, like a few hundred simultaneous users or a few hundred independent sessions that have independent Julia sessions, and it's working okay. And I think even this weekend there's an experiment to push that up to a few thousand and see how it performs. So that's what it's doing. It's calling sessions, and each session has its own sort of little Julia sandbox to work in that it starts up, and then it solves problems against that. So when you're working with this kind of distributed set of things, when you have some people who are working on the front end in JavaScript and other people who are working on Julia code, so on, you sort of need this distributed team. So one of the things this is actually the team that worked on this little example that I showed you. So there's a UI designer, there's a modeler, or a data scientist, a web developer, a person in QA, and then someone who's managing the project. So it's a quick project, but you sort of need a team of people to come together to put this all in. And I thought it would be interesting to see from the perspective of the tool how that all works. So here it is. This is the project file, and in here you have personal project, but also team-based things. And there's the route optimizer team, right? And so in the route optimizer team, there are a number of team members that have access to a particular project at a time. And then in here too is code. So if I look at the Route Optimizer project, what I can see is the static code, which is, oh sorry, that's not where I want to start. The model code, which is these two model objects I mentioned earlier. This is the TSP model here that pulls the solver, and here's tsp.jl. And then there's some static code in here too for, basically it's just JavaScript code and HTML and CSS and that sort of thing. So if I look, for example, at data, and I look at, say, book crawl, then I can just see this JSON file of book stores in San Francisco with their latitude and longitude. And this doesn't need to be, this can be served or hosted on Epicenter, but it doesn't have to be. Obviously, all this code could sit on a separate server and just call the model service separately. So that's the basic idea of it. Let's see. And in addition, there's this concept of dedicated compute units, which is similar to ECUs, I guess, in Amazon. The idea is that, what you're trying to do is figure out like what's acceptable to a user, like how much time can he or she want to spend on waiting for a result to come out. And one way to solve that problem, there's multiple ways, of course, but one way to solve that is to up your computing units or use virtual compute units to do so. But for this very simple problem, it's not necessary. There's other things with the API keys and transferring things and so forth. So that's the basic idea. This is kind of the start. What we've been focusing on so far are these base APIs. And we've gotten up to the point now of getting to this JavaScript library. So we have the stack available. What we're trying to do is move away from a little bit of this issue of, you need a big team to put something like this together to make it something that's more accessible for a single individual. And so our plans for the platform at this point is to get up to being able to provide this user interface designer. And so far we've been using this in a few projects. We've built this out so that we have it available in some things for Harvard Business School. We've been doing some projects with Julia for them, where they've been using it mainly for MBA students, not only for their own school, but for other schools. We've done some data analytics and forecasting projects using it. A year from now, we should have some nice examples built out from what I've shown you so far with this route optimizer and something that's less of a demo case and also machine learning problems. So, to summarize, we're very happy, and I think we have, internally, I can tell you we have a lot of enthusiasts for Julia. And the things that people like about it that come to For You and then learn about it are that its expressiveness is helping a lot in terms of internal adoption and, of course, speed. But I think a big part of it, too, is the community, is being able to share things online, being able to go to the users group and to see these dozens of daily updates and things like that. So this platform we're going to be releasing very soon. And by very soon, I mean a matter of days. We should have it out next week sometime. And sort of other big message from us, in terms of the production-based stuff, is that we're seeing Julia being used in production, and its customers are pleased with it. So if you're interested, you can try this out. You can go to foryou.com/epicenter. Right now, it's still in beta invite mode. So if you would like a code, let me know. But after next week sometime, you should be able to access it directly. Thanks.
We have plenty of time for questions.
I have two questions, but I'll ask one for the moment. Which is that, how do you interface with the web server? Are you using a Julia web server or putting a Julia cluster behind?
The web server is partly powered by Julia. And so there's an issue. Are you talking about like how do you scale up sessions and things like that? Is that
just the stack.
Yeah, the stack, it's a complex stack with a lot of different technologies. So we have some Lua behind it, some Java. We have obviously a database that's running on it as well, and some Julia code directly that's actually managing the server. So that was an experiment with us, and obviously there's people internally who are enthusiastic and sort of looking at ways of using Julia as a server language as well. So, there's a lot of Julia. Obviously, is pretty young still, so I think it's worked out reasonably well for us. We're pleased with it, and like I say, we're ready for production. Any other questions? Yeah.
So you said nice things about what you like about Julia. So what don't you like about Julia?
Very little, actually. I mean, you know, it's early on, right? So it's early language. So, you know, the same things that Avik had pointed out regarding version issues, we've hit too. And I think we've sort of dealt with it in the same way that you have, in that recognize the fact that it's a new language and that these things are going to be moving, and we're not at 1.0 yet. So, you know, we just have to adjust things and move forward, and that's been okay. I think the big thing, you guys might have noticed it actually when I was running it. I'm not sure it's a big thing. It's a problem to be solved, right? So that's kind of the issue. Like, but if you go back to this solver, you know, so what's happening behind the scenes, right, is we're creating an entirely new instance of Julia on a server every time we create a new session. So let me create a new session here. Yeah, exactly. That's right. That's pretty obvious. So let's go. So here's the JuliaCon route, and here's sort of that lag. You can see it right now. It's evaluating, and what it's doing is it's setting up the server. And the issue is not entirely, but mostly with Julia starting up. That's most of the issue. But once it started, it's beautiful, right? So once it started, it's like it goes, right? So it's kind of the same point that you all have made in forums and elsewhere, right? But on the server, it's a little bit different, a little bit different experience. And we've done a lot. We've worked hard to figure out how to speed up. We're trying to do everything we can to cut that down. I mean, when we first started, it was like, in worst cases, like 30 seconds. That's completely unacceptable for a web server. It's kind of getting back to my point about speed needs that are a bit different with web servers.
So you're pre-compiling a lot of the packages?
Exactly.
Yeah.
Yeah. That's the approach we take in. You know. So.
But even then, you have this delay, even with the pre-compiling.
Well, yeah. But I mean, it's not terrible. I mean, it depends on how you look at it, right? It's probably, what is that, 2 or 3 seconds? Something like that. Maybe a bit longer. I don't know.
Like 5 seconds.
I mean, pre-compiling doesn't really pre-compile everything, right?
Right.
I mean,
Yeah.
you still have to JIT code.
Yeah.
I mean, if packages start like shipping a file that includes a bunch of precompiled statements, that's like the common functionality.
I've played with that a little bit, and but you have to pick which types you want to
Yeah.
precompile
Right.
for it to be useful.
It might make sense to have like an observation mode where Julia just basically, like you run your typical workload and then we look at what functions were compiled and just dump all of
That is
those
a good idea.
to a file.
So first thing you could track is sort of like the stats about what's used.
Yeah.
Yeah, that's a good
And
idea.
then I guess you could do that.
And then you just put it into your __init__ function.
Yeah, something with like even just having it in the cache or something.
Another idea would be you could maybe just have the process already started and fork it.
Yeah. That's interesting. Yeah.
But it has to go into a separate sandbox, though, right?
Assuming he's not using sockets or anything.
I don't know what the setup is, if that's even possible, but that would be, you're basically cloning a pre-started.
What instance are you starting up?
We're using Docker for, is that what you mean? Or?
Yeah.
Yeah. So that's the technology we're using with some other stuff too.
Docker on EC2?
Exactly.
Okay.
Yeah.
So you're firing off a new instance every...
We're not starting a new server each time, but we're starting sort of a virtual server via Docker in a single, yeah.
But with Docker, you could easily cache the like pre-started instance.
Yeah. It's I'm not sure. Like I don't know enough about the I know the team has been working hard on the specifics of how to do that, but that's something I'll relate
There's
back
also
to.
Docker Julia package.
That's right. I saw that. That's right.
It's written by guess who?
We're doing something like, just to explain, we're doing something similar at MIT, or we were doing something similar at MIT, where students could log onto a web service and they'd get a Dockerized notebook. We might get back to doing that. The MIT is nice because all the students have a SSL client certificate, so I didn't actually have to write like HTTP redirects. I could just like handle all the authentication in the transport layer, which makes it really easy to do this kind of thing. But yeah.
All right. Thank you.